In this presentation, I'm going to talk about how to differentiate between convex and concave function. So let's start. So let's start with the definition of a convex function. Suppose we have a convex set S and then we have 2 points in that convex set. So let's say we have x prime and also we have x double prime on the convex set S. And then we say this function is a convex function if it satisfies this, which means that the function value of that point itself is always smaller than or at least equal to the value of the linear combination of the function value of point x prime and the function value of the point x double prime. So we put these two things here, the constant c and the 1 minus c. Remember that c must be between 0 and 1, including 0, including 1. So let's see the image to see how it works. So let's say we have 2 points. One is point here x prime and the other point is here x double prime. And then we have a point between them. So this point in the middle is calculated using c times x prime plus 1 minus c times x double prime. So it's a linear combination between x prime and x double prime. So we have the point x, we have the point x double prime, and then we have the point between them. Now let's see the function value for each of those points. So for the first point x, the function value is there at point A. For the second point x prime, we have the function value is point D. For the value in between x and x prime, the function value is here B. Now what this is saying is that if we take the linear combination between the value of this A stat and then D is up there a little bit higher, and then the function value of the linear combination. So imagine you draw a line between A and D, and then at this point in the middle you see that this part on the right hand side is point C. It is higher than the actual function value, which is at point B. That's why this function is called convex, because the actual value of the function is always smaller than or at least equal to the value if you take the linear combination of them and then check at that point what is the value of the linear combination. So this is called convex. You may think of this function as something like the alphabet V, because it is convex. Okay. So for concave function, it's the other way around. So we see here that for concave function, the function value of that point, which is the point between x prime and x double prime, is always greater than or equal to the linear combination of the function value at the point x prime and the function value at the point x double prime. Remember, here to get the linear combination, you need to use c and 1 minus c with the restriction c is between 0 and 1, including 0 and including 1. So let's see the graph. So here we can see that we have this point x prime, we have this point x double prime, and a point between them, which is the linear combination between x prime and x double prime. The function value of x prime is here, A. The function value of x double prime is here, the point D. And then the actual function value for the point in between them is here, up here in the point C. However, if we take the linear combination, which means again like you draw a line between A and D, and then you check what is the value at this point here, you see that the value is much lower than the actual function value at that point, which indicates that this type of function is a concave function. You may think of this function as like an alphabet A, so it's concave. Now we have three examples here. The first example is the function of x squared. It is a convex function. It's like a alphabet V, and you can see that if you take any 2 points and then you draw a line between them, then let's say this is the point at 0, you can see that the actual function value is lower than if you take the linear combination of the other 2 points. So that is the indication of a convex function. Same here, e to the power of x in the second example, it is also a convex function because with the same reasoning, if you take 2 points and then you, sorry, it's not a very good line, but you can imagine if you take a straight line between 2 points, then the linear combination of that 2 points is always higher than the actual value of the function at that point. Now the third one is a concave function because if you take 2 points, let's hope that my line is better here. So this line, this point here and that point there. And then if you take a straight line between them, and then let's say you check at this point, you can see that the actual function of the value is higher than the linear combination of the 2 other points that you get. Okay, so it indicates that this is a concave function. Now, the sum of 2 convex functions is still a convex function. Similarly, the sum of 2 concave functions is still also a concave function. Now, it is also possible that for a certain range of the domain of a function is neither convex nor concave. So for example, if we look at this range of x here, you can see that at that part, the function looks concave because the actual function value is higher than if you take the linear combination of 2 points. However, if we look at this second range of x around here, you can see that the function is convex because the function value is always lower than if you take the linear combination of 2 points. So here you can say that this function is neither convex nor concave. Now it is also possible that a function is both convex and concave. The example for this kind of function is a linear function. So if we have a function that is both convex and concave, it means that the function value of a point is exactly the same with the linear combination of 2 points. Okay, so if you take a point which is the linear combination of x prime and x double prime, then the function value is also the linear combination of the function value of x prime and the function value of x double prime. If it is exactly the same, it means that this function is both a convex and concave function. Now, why do we care whether the function is convex or concave? Well, in the case of NLP, it helps us to identify the optimal solution. So suppose we have a maximization problem, and then suppose again the feasible region is a convex set, and we call that region S. If a function is concave on S, then any local maximum is an optimal solution to this NLP. So if we know that the function is concave in the feasible region, And then we know if we already get a local maximum, then we can say that that point must also be an optimal solution. Similarly, if we have a minimization problem, and then the feasible region S is a convex set, if the function fx is convex on the feasible region, when we find a local minimum, it means that that local minimum is the optimal solution to this nonlinear programming. Now suppose we cannot draw the function. How do we know if a function is convex or concave? So we can use the second derivative of the function to determine whether a function is convex or concave. If the second derivative is greater than or equal to 0 for all x in the convex set S, then we can say fx is a convex function. So the meaning of the second derivative is the changing of the slope. Remember that the first derivative talking about the gradient or the slope, and then the second derivative talks about how much the gradient change or the slope changes. If the second derivative is greater than or equal to 0, it means that the slope keeps getting more and more and more positive, or at least 0, which means that the slope is non-decreasing. Let's see an example here. Suppose we have a function that looks like this, the x square function. At this point, the slope is very negative. And then if you go right there, the slope is still negative, but less negative than before. Or in other words, it's getting more positive. Here, it's still negative, but it is getting closer to 0. At this point, the gradient is 0. And then at that point, the slope starts to become positive. And then up here, it becomes very positive. So you can see that as the value of x goes from negative to positive, you can see that the slope keeps getting more and more positive, or in other words, increasing. So we can say that the second derivative of the function x for all x is greater than or equal to 0. And this indicates a convex function, because you can see that the slope is going from very negative to close to 0, 0, and then becomes very positive. So the slope is non-decreasing. It becomes more positive. It's the other way for a concave function, which looks like this. You can see that the slope is non-increasing, because first the slope is very positive, this point, and then here is still positive but becomes less positive, closer to 0, and then at the peak the gradient is 0, and then here it becomes negative, then down here it is very negative. So the slope keeps decreasing, more and more negative. So when it is say f double prime x less than or equal to 0, it means that for this function the slope is non-increasing. Now we have 4 examples here, and then for each of these functions we need to determine whether it is a convex function, it is a concave, or both convex and concave. And then for each function we have the domain. This is the real number R1, this is real number, this is between 0 to infinity, and then the last one is again S is equal the real number. Although we may draw the graph for each of this function because it contains only one variable x, but here we are going to use the second derivative to determine whether a function is convex, concave, or both. So the first one is x squared. We take the second derivative of this function, we get f double prime x equals 2, which is greater than or equal to 0. So this is a convex function because when the second derivative is greater than or equal to 0, it says that the slope of this function is non-decreasing. So for x squared, we can see that the slope is going from very negative to 0 until very positive. So it is a convex function. Similarly, for the second function, e to the power of x, we take the second derivative of this function, which is still e to the power of x. And then whatever the value of x is, positive, negative, 0, e to the power of x is always greater than or equal to 0. So the function fx is also a convex function. For the third function, x to the power of a half, we take the second derivative, we get minus x to the power of minus 3 over 2 divided by 4. And then if we put the x between 0 to positive infinity, we always get a less than or equal to 0 value. So it means that fx is a concave function. Now, the last function is a linear function. So if we take the second derivative of this function, we get the value exactly equals 0. Because the value is exactly equals 0, it means that this function is both convex and concave. So that's how we are using the second derivative to determine whether a function is convex or concave.